So this is how the Tesla Cyberquad comes from the factory. Let's fix the spec sheet a little. Battery voltage, 36 volts? That's cute. Let's make that 72. Motor power, 500 watts. Let's add a 0. Top speed? Yeah, we're not spoiling that yet. High and low speed mode? Let's rename those to fast and probably too fast. Range? Technically, it depends how you drive. LED headlights and taillights? Sure, but now they're RGB. With that spec, we should probably also change the recommended age. 9 to 12, let's call it 16 to 120. One more thing, I'm not loving the photo. There, much better. The first real job was figuring out how to mount the new motor. This was definitely not a drop-in replacement. The stock motor is smaller, simpler, and fits the factory mount the way Tesla intended. The new motor had other plans. So the first step was extending the original mount with an L profile, because the new motor needed to sit farther out than stock. From there, I cut new slots into the mount, using a 3D printed template based on the new motor's bolt pattern. After some fine-tuning, I could test fit the bolts and make sure everything actually lined up with the motor, and check that the motor moves smoothly in the slots. That adjustability matters, because later on, that's what lets me tension the chain properly. With the motor mount in a good place for now, it was time to figure out the brakes. The stock brakes were one of the things I already knew I wanted to improve. They weren't great to begin with, and even finding replacement pads for them is kind of annoying. So I bought a different caliper that looked like a much better option. And at first, this actually seemed like one of the easier parts of the build, because the new caliper fit the original mount without any extra work. The problem was the original brake disc was too thick to fit inside it. Luckily, I had another rotor lying around that was thinner, so it looked like that might solve the problem. It looked like an easy fix, which should have been my first warning sign. I pulled the original disc off, test fit the thinner one, and of course, the bolt pattern didn't match. So now the caliper problem was solved, but the mounting problem had just started. Since the rotor itself was the one I wanted to use, the fix was to modify the hub side mount to match it. And to do that cleanly, I made a little marking tool on the lathe that fit the rotor holes exactly and let me mark the center of each new hole precisely. First, I marked the general area in blue, then used the little jig to transfer the exact center of the hole onto the mount. And this part actually mattered. I didn't have a spare mount sitting there in case I messed it up. If those holes drift even a little, the rotor ends up crooked, and now, instead of fixing the brake setup, I've created a completely different problem. Once I had the center marked, I punched it and drilled the first hole, which is where the mount reminded me that freehand drill press work is just gambling with extra steps. After that, I tapped the hole for M6, bolted the rotor down through that first position, and used it to lock the pattern in place for the rest of the holes. Then it was just the same process a few more times. Mark, drill, tap, and in the end, it turned out not too bad. Once the machining was done, I cleaned everything up to get rid of the oil, chips, and whatever else was left from the process. Then I bolted the rotor on for real with thread locker, because brake hardware is not the place for "it'll be fine." With the modified mount finished, the new rotor finally went onto the axle the way it was supposed to. And since the caliper itself fit the original Tesla mount without any extra work, that part was basically plug and play. And with the brakes finally sorted, I could move on to the controller. This is the part that sits between the battery and the motor and controls how the motor actually behaves. Since there wasn't some obvious place to mount it cleanly, I made a 3D printed bracket for it so it could bolt into the frame properly. This was one of those parts that needed to fit neatly from the start, because once the controller position is locked in, the rest of the main wiring starts getting built around it. Right below that, I added an aluminum battery plate to spread the battery load across the frame a little better. The pack for this build is not exactly small, so I wanted that weight supported properly, instead of hanging all of it off a couple of tubes and hoping for the best. Once the controller was in place, I could start laying out the main power path. And because everything in this area was packed in pretty tightly, even the main terminals had to be reshaped to fit cleanly. This is the kind of work that doesn't look dramatic, but it matters. High current wiring needs to fit the space without being forced, twisted, or constantly under stress. Before crimping the main cables, I also used conductive carbon paste on the wire ends. The goal there is to improve the contact between the wire strands and the terminal, lower resistance, and help keep the connection cooler under load. Less resistance means less wasted power turning into heat, which is exactly what you want in the part of the system carrying the most current. I also added a T-class fuse into the main battery line. This is not just a random fuse thrown in for decoration. At this voltage and current, you want something that can safely interrupt a serious fault if something goes wrong. If there's a bad short somewhere in the system, this is the part that's supposed to fail first, before the battery turns the rest of the wiring into a much more exciting problem. So from the controller, I built out the main cable path through the fuse and toward the battery connector. And then there was the battery. What you're looking at here is one side of the battery enclosure. I designed this pack specifically for the Tesla Quad, around the space I had to work with. Each of these cells is 3.2 volts, 15 amp hours, and rated for 75 amps continuous. I went with lithium iron phosphate cells here because I trust them a lot more for something that's living inside my garage. With 24 cells in series and 2 in parallel, that gives me a 72 volt pack good for 150 amps continuous. This is the BMS, keeping an eye on the cell groups, balancing them during charging, and shutting things down if anything starts going out of bounds. I used multiple layers of copper bus bars throughout to keep resistance low, and spent way too much time on wire routing, because if I was going to build a custom pack, it might as well look nice, at least from the inside. Because once everything was wrapped in fish paper, Kapton, and black tape, it started looking less like a battery and more like something TSA would have a lot of questions about. But with the pack finally done, I could test fit it in the quad, cut the cables to length, and for the first time, the inside of the quad went from completely empty to basically out of room. With the controller mounted, the battery in place, and the main power wiring roughed in, I could finally start dialing in the smaller details. One part I did want to get right was the charging port, so naturally I started with some extremely advanced CAD, cardboard-aided design. Once the shape looked right, I marked it onto the plastic and committed to cutting a hole in a perfectly good body panel. This is one of those moments where you really want to be right the first time, because plastic has this annoying habit of not growing back. Once the opening was cleaned up, the port dropped in nicely and finally started looking like it actually belonged there. After that, there was still a ton of wiring left to do. And to be honest, neither of us needs a 20-minute montage of me shrinking heat shrink and chasing wires around a tiny frame. So instead, let's jump to one of the more interesting electrical parts of the build, the custom brake controller. The stock Tesla Quad has a rear light that works kind of like a car. It stays on as a taillight and then gets brighter when the brake is pressed. But because I wasn't using the original controller, that feature was gone. So if I wanted that stock behavior back, I had to build it myself. I started by mounting the PCB blank onto this aluminum fixture plate. The nice thing about this plate is that it matches both my fiber laser bed and my CNC bed bolt pattern, so I could move the board between machines and keep the exact same position the whole time. With the board locked in place, the fiber laser cuts away the unwanted copper and leaves behind the circuit traces. I could watch this all day, but only through a camera, because this thing can turn "that looks cool" into "why can't I see" real quick. After that, I moved on to the solder mask. I taped a piece of screen printing mesh over the fixture and used it to spread the UV mask evenly across the board. Then I peeled the mesh back off and left the board with a clean, even coat of solder mask. Once that cured, I used the laser again to clear the solder mask back off the pads so the components could actually be soldered on. And if you're following at home, the fumes from this whole process are seriously toxic, so you need real ventilation, not just an open window and good intentions. After that, the whole fixture moved over to the CNC so I could drill the holes. At that point, it was finally starting to look like an actual PCB. Then I applied liquid tin, which protects the copper and gives the board that nice silver finish instead of bare copper. Now, the keen-eyed people probably noticed that the boards I've been showing here aren't all the same exact iteration. And that's because this was not exactly a smooth sailing process. It took me at least 5 tries to get this board right. Some versions failed at the laser stage, some during solder mask, and some waited until final testing to disappoint me. So this definitely wasn't one of those magical first-try PCB stories, But eventually, I got a version that actually survived the whole process. Once I finally had a good board, I could solder on the components, wire it up, and see if this thing actually did what I designed it to do. And this was the first real test. The brake handle on this quad doesn't use a simple switch, it uses a potentiometer, so it outputs a changing voltage depending on how hard the brake is pressed. And it also sends a brake signal to the far driver so brake and throttle can't be applied at the same time. I still had to tune the analog input in the code a bit, just by checking the brake values at different handle positions and adjusting the thresholds until everything behaved the way I wanted. Once that was dialed in, it was time to make an enclosure. I 3D printed a simple case, added some threaded inserts, and sealed the board inside with hot glue. I cleaned up the glue residue with IPA off camera, mostly because that is a lot less exciting than it sounds. Then it was just a matter of drilling a small hole for the LED strip wiring into the controller compartment, plugging a few connectors together, and putting the plastic covers back in place. Done. Well, almost done. Because even though everything was installed, there was still one very important question left. Would any of it actually work together? Now it was time for the far driver auto learn, the moment of truth. First, I plugged in the battery. No explosion. Excellent. Then I powered everything on. Still no magic smoke. Even better. After that, I set the motor parameters in the app and kicked off the auto learn. That's the process where the controller spins the motor, reads the Hall sensor feedback, and teaches itself what it needs to know to run the motor properly. And since nothing caught fire and I was still standing there, I'm calling that a win. With that out of the way, it was time for final assembly. And just like that, it was out of the garage and moving under its own power. At least, mostly. Pretty quickly, I ran into an issue where the quad would stutter when I got on the throttle. It turned out the brake controller was getting triggered by electrical noise from the motor, which bumped the analog reading just enough to make it think the brake was being pressed. The fun part was that it was intermittent, so sometimes it would do it, and sometimes it would work perfectly. The fix was simple. I disabled the brake signal going back to the controller. I cut that wire off camera, which does mean brake and throttle can now be applied at the same time. But on the bright side, that is a lot better for wheelies. From this point on, the quad was actually being driven by my friend. He is a lot less attached to being alive than I am, so he has become a very useful part of the testing process. I handle the building, and he handles the part where we find out if I forgot something important. And honestly, aside from the brake triggering issue, the rest of it went great. The quad felt solid, tight, and way better than it had any right to. So from there, we did the only sensible thing. Drove it around, took it off-road a bit, got some drone shots, and generally enjoyed the fact that it actually worked. Now, I should probably come clean about one thing. This is not actually the first upgraded Tesla Cyberquad I've built. It's the third. The other modified one you saw earlier in the video was my original build. The second one has already been sold, and this one was actually spoken for in advance too, so it is no longer mine either. But before it left, we had to answer the important question. How fast was it?
And yes, I already know what some of you are typing in the comments. 41 on a kid's toy? That's not even that fast. Apparently, the cop agreed.
But trust me, I have already experimented with faster setups on these quads, and at some point, more speed just turns into more stupidity. They already have enough torque to do things they absolutely should not be doing. And for something this small, it pulls way harder than people expect.
1.
It even gave a Tesla Model 3 a respectable run for its money, at least for a little while.
It's the same.
This is just the beginning. I've already got more projects in the works. Faster carts, bigger battery packs, smarter electronics, and a few builds that might even be genuinely useful. Some of them are built for speed. Some are built to solve real problems. So if that sounds like your kind of thing, subscribe. And if you enjoyed this one, hit like so YouTube knows this is worth showing to more people. I'll see you in the next one.